what I wanted to do was look a little bit at the next chapter, which is sort of like it's not really a topic. It's like a foundation for the next chapter, eigenvalues and eigenvectors. It's on complex numbers. And I want to explain why we need complex numbers. So in the next chapter, we're going to have to factor polynomials. In principle, either really or factor them. And the point is that I can have polynomials like this that are going to result from doing eigenvectors and eigenvalues. Well, so here's an equation you want to solve for x, right? Well, obviously there's no real x that goes in here, so you have to use x equals plus or minus I, where I equals the square root of minus 1. Okay, so the problem is we want to be able to factor this x squared plus 1 equals x minus I and x plus I, because that would be x squared minus ix plus ix and minus I squared is minus 1. You get a minus sign, so you get plus 1. So this enables us to factor this polynomial. Now, there's a theorem that says any polynomial can be factored into a product of linear terms like this. So I take any polynomial, and if I allow myself to use the complex numbers, the only thing that I need is I'm going to have this factor like this. Now, it turns out that if I take any polynomial and I try to factor it, I'm going to get linear terms with real numbers. And if I get a complex term, I'm going to get like one like plus I and one like minus I, right? I'm going to get a plus. So there's always the only thing that real numbers can't do is the quadratic equation. It's not like there's some kind of weird x to the fourth equation that's going to come up that you can't factor. It's always going to come down to linear factors with real numbers sort of in the slots here, or pairs where you have two complex numbers being numbers that have a square root of minus 1 in it. So now these two numbers are called complex conjugates. And you know the general complex number z is equal to x plus iy, right? This is a motivation. This is why we need complex numbers. Now, the only reason we need it is to be able to say, okay, with any polynomial, which is going to come in the following chapter after the complex number chapter, that we have to be able to factor the linear factors. You can't do that with the real numbers. So that's why we'll say, okay, we're going to use complex vector spaces where the numbers and the entries of the column vectors will be complex numbers. But we're not actually going to use complex numbers. We're just going to use real numbers. And then we need this to know that it's possible to have them reappear in this circumstance. And since we're actually going to choose, so I'm actually going to try to choose matrices for which this doesn't happen, you will likely not see any complex numbers. So the point for mentioning them is so that to explain what the real picture is. So if you go to another text or another context, you'll realize, why are they saying complex vector spaces? That's just vector spaces where in the columns you have complex numbers. And that's sort of the motivation. But I wanted to show you, and so you may sort of wonder, well, this is sort of might have been always mysterious, right? Because it doesn't make any sense, right? You just added it as if, and it says, okay, everything works out. But on the other hand, though, you've also seen that you started like in elementary school with the integers, and then you can see that you can make the fractions as ratios of integers. You can sort of construct them with pairs of integers. Go ahead.
So this, I think I remember. So this has to be like I equals the square root of -1, and I squared equals -1.
Right.
I cubed equals negative squared -1, and then I4 equals 1, and then anything that's a multiple of kind of just.
No, you can keep dividing it up, because you could do like I to the fourth would equal I squared times I squared, which equals -1 times -1, which equals 1. So there's and the question is, why does this occur, and what's going on? Well, so that this is the general pattern, and you can say, well, if I have this, then I have something. The complex conjugate is x minus iy. I'm doing this for a reason, not just to. I want to show you something about how you can. I was telling you that you can construct the fractions, rational numbers, from integers, and then you can construct the real numbers as sequences of rational numbers that accumulate at a certain point, so that you can sort of say, okay, every real number, you can think of this as a decimal expansion, that you can think, okay, I have to have an infinite number of terms, because I'm saying, okay, I have to be able to decide on each scale how I'm going to measure it. So the real numbers you construct as sequences, but then probably you haven't seen a construction where someone says, well, how do we construct the complex numbers out of the real numbers? Then it would sort of make sense. It wasn't just like someone said, look, if we introduce this weird number, square root of -1, we can solve quadratic polynomials and everything works. And you say, okay, and then you can either sort of accept it and move on, or sort of be puzzled, well, where did that come from? You know, can you just, you know, and that's what people did in the 1800s. They asked, well, are there more things you can add to get more numbers? And this guy named Hamilton came up with quaternions, where you add the square root of minus, you have I squared root of -1, for you have an I, J, and K that are all I squared is -1, J squared is -1, K squared is -1, and they're not equal to each other, and they have weird products. The problem is that they don't commute as numbers. You have a non-commutative system of numbers. So they weren't really happy numbers. They were sort of only part of the properties, but somehow real number, complex numbers seem to have all the properties except for ordering. You know, real numbers, there's like larger and smaller. With complex numbers, you don't have this notion of larger and smaller. So because they're disordered, and because everyone has two numbers, usually, if you've seen this before, you probably have seen these numbers written as where you can associate them as like a vector in the plane. Okay, so and also they have a magnitude, like the magnitude of z squared equals x squared plus y squared. Okay, now so you have so you have the magnitude of z equals the square root of x squared plus y squared. Okay, so now what I want to do is show you, let's take the complexness, let's take the following set Z of 2 by 2 matrices of the form x minus y, such that x and y are any real numbers. Okay? Well, this is a vector space, and I'm going to claim these act entirely. They are the real. They are the complex numbers. They act entirely like the complex numbers. And so the crucial thing is when I multiply 2, say x1 plus I y1, x2 plus I y2, and you use this rule of the square root, you can write, okay, well, this is going to be x1, x2. Then I'm going to get a real term from minus y1, y2, right? Plus I times y1, x2 plus x1, y1, okay? I just multiplied out x1, x2, that's this one. Then I times y2 times I times y1, I get a minus sign from this I squared y1, y2. Then the cross terms, the I doesn't go away, I have y1, x2, and x1, y2. So it's this weird product, right? It's like, okay, it makes you unhappy because it's like, why did it have to be so complex? Okay, but now what I want you to see is, let's say that I had two of these numbers, x1 minus y1, y1, x1 times x2, x2, y2 minus y2, and just do normal matrix multiplication. Okay? Well, let's see what the result is. Well, it's going to be x1, x2 minus y1, y2 for this term here, the first row times the first column. Then the second row, the first row times second column will be minus x1 y2 minus y1 x2. Then down here, the second row times this will be y1 x2 plus x1 y2, and the second row times the length column will be minus y1 y2 plus x1. No, it'll be y1 minus y1 y2 plus x1 x2. So you notice, this is the crucial thing, that when I do this, I get something that's of the same form. I get something where this term is identical to this term, right? See, this has got a minus sign for the y1, y2, this is a minus sign there. This one is minus, let me just write it out, x1, x2 minus y1, y2, and down here, x1, x2 minus y1, y2, minus x1, y2 plus y1, x2, and x1, y2 plus y1, x2. So this is of the same form. So this is the nice thing. If I take matrices of this form and matrix multiply them, they're exactly the same form. And I don't think this happens for any other matrix, for any other matrices of any sizes. This is what makes the complex numbers possible. And you notice that the product up here, this term, this, when I looked at this product here for this equals, you see this is the same as this term up here, right? And the term over here is the same as here. So this suggests that x minus y, y, x, if I decompose that into a basis, right? What do we usually do with a basis? In fact, I pretend y is 0 and say x times 1, 0, 0, 1 plus y times with x 0, 0 minus 1, 1, 0. Well, this looks a lot like z equals x plus iy. So what I do is I say, well, this is like my 1, right? And this is like I. So if I do minus 1, 1, 0 times 0 minus 1, 1, 0, that equals 0 equals 0 times 0. There's a minus 1 there, right? And this one is 0 times minus 1 plus 0 times minus 1. This is 1 times 0 plus 0 times 1. And the last one is 1 times minus 1 is minus 1. So if this is I times I, this is like minus the identity, which we treat as 1. So what happens is then that and then you can ask, well, what about the complex conjugates? Well, let me see, here, so if my z, so to speak, is x minus y, x, then z star, the complex conjugate of that, should just change the sign of the y, right? up here. So the complex conjugate just changes the sign of the y, right? So if I choose this and I just change the sign of the y, this equals Z transpose. So the transpose is the complex conjugate. Okay. What about, here's the interesting, so this magnitude here is also, it turns out that Z squared equals Z times Z star. Okay. Well, let's first of all take the determinant of Z, okay? This matrix. So that's x squared minus x times x minus the product of these minus y times minus y, which equals x squared plus y squared. So this was the square, this is the square, this is, so that rather, the determinant is the square of the magnitude, right? So you end up with both the transpose and the determinant working nicely with all the things you usually define with the complex numbers where you just treat it as I minus one. So, and then you can sort of see that if I take Z times Z star, which is x minus y, x times x, y minus y, x, here, the matrix times its transpose, then that's going to equal x squared minus y times minus y plus y squared, and then xy minus xy, and then yx minus yx, and then y squared plus x squared. It equals x squared plus y squared times 1001, which is if then if you're thinking of this as sort of the identity, then that corresponds to what's happening up here with Z squared equals Z times Z star, which is the complex. So the whole thing works in the sense that you can say that the set of matrices of this form are, you can just think of them as the complex numbers. So the complex numbers are not just, they're like these two by two matrices. But what do these matrices do? Well, what happens if I look at the coordinate axes here, x and y, and I look at, say, an x here, and there's an x and a y here for some number z, and I want to treat the hypotenuse as the length here is 1, right? Well, what are the special numbers that have length 1 here? Well, that's going to be x is going to equal r cosine theta, and y is going to equal r sine theta. So if this r is 1, that basically means that's going to be like a complex number of length 1, magnitude 1. If I do that, what is the complex number? Well, it's basically going to be cosine theta minus sine theta, cosine theta. Well, what this is the formula, this is the matrix that implements a rotation by the angle theta in 2 dimensions. So, and you can see then that I can write any complex number as r times cosine theta minus sine theta, cosine theta, right? So you can see that the complex numbers are really basically rotations in a two-dimensional plane, and then scalings, making them larger and smaller. So that's why they have a lot of the weird properties they do. Now, one of the things you can ask is, well, what happens when I have, if I have the number I here, that corresponds to this being 0, 0, 1, and 1. Well, that corresponds to theta equals pi over 2, right? This would be 1, 1 minus, so, and an R here's 1. So I equals cosine pi over 2 minus sine pi over 2 sine pi over 2 cosine pi over 2. So then if we look at the plane and we think x, y, and we start with the vector 1, 0 here, right? So this is our vector 1, say. This is like a 1 on the real line. Well, what happens if I multiply this by I? What I'm doing is I'm rotating it into this direction. So I can think of, well, if I want to rotate this 1, I'm going to rotate it into an I here. So I can map, and then I can, if I do another rotation, I'm going to map that out to where it's -1. And if I do it a third time, I'm going to map it down here, and it'll be -I. And I can do this, I can just keep rotating around the circle, and that's what your formula for I to the fourth, or it's different. I can just keep multiplying I and keep rotating around the circle here. So you can think of I as just a rotation by 90 degrees. So using the introduced complex numbers, you just say, okay, the points on the plane are complex numbers. It's called the Argonne plane. You just think of the complex numbers as this 2x2 plane where each point is a complex number. But you can also think of them as just the Euclidean plane, and the complex numbers are rotations. And then you can just associate, okay, well, when is the place I get to when I rotate by 90 degrees or by a certain angle? So you can get out this you can connect up the geometrical interpretation of complex numbers with the realizing that complex multiplication is just the ordinary matrix multiplication of 2x2 matrices makes the complex numbers less mysterious. The reason they seem mysterious when we write them as individual numbers is because they're really 2x2 matrices that you've encapsulated in these formulas of I squared equals -1. Okay? So there's this hidden structure, geometric structure, and algebraic structure that makes sense in terms of linear algebra and matrix multiplication, but that's mysterious if you just treat it as, let's just introduce these. The historical is sort of like the historical stream discovered the complex numbers before doing all the linear algebra stuff. So the connection wasn't completely clear. People did make the connection between the geometric stuff, but then it's still presented, like if you go to a complex, a textbook where you use complex numbers, they'll introduce them in the historical order of saying, oh, well, let's just make it so we can solve quadratic numbers, and look, everything works, and just explore the algebra of how it works and then the geometry. But then if you look at it this way, you sort of see that there's a much more internal coherence to the complex numbers making sense. And the fact that it doesn't work for any other form of matrices means that something with the complex number is special, because there's no other, it doesn't work for 3x3 matrices. The quaternions sort of work for 4x4 matrices, but they're not commutative. And you've got something called the octonions, which are even worse because they're not associative. So, and they're like 8x8 matrices or something. And the product is not the matrix product, because it's not associative, and matrix products are associative. So there's something special with the complex numbers, and so anyway, this is really all I wanted to say, and the whole point of the complex number chapter here.
Is this related to Euler's formula at all?
Yes. Euler, how do you say that? Euler's formula.
Either the IX or F theta.
was that e to the I theta equals cosine theta plus I sine theta, right? Well, you notice that, and then up here, what's happening is that so let's see, what does this correspond to? If I treat this as cosine theta times I plus sine theta times 0 minus 1, 1, 0. And this is the identity, this is going to be then cosine theta, 0, 0, cosine theta, plus 0 minus sine theta, sine theta. So then you end up with e to the I theta equaling the cosine theta minus sine theta, cosine theta. Well, this is just a rotation by angle theta. So, and this is what this is. So now, in some sense, then, if you want to connect up like this form here, the problem is that how you, like, here, let me see. The secondary thing is, this is works, but the problem is, how do you define e to the I theta? Well, that's going to be an exponential function, but then you have a 0, minus 1, 1, 0. You have a matrix and an exponent. Well, how do you define that? Well, you have to define that by a power series exponent of the exponentials. So there's a connection here, but the connection has to do with calculus in the sense that e to the x equals 1 plus x plus 1 over 2 factorial x squared plus 1 over. There's a Taylor, I don't know, you've seen Taylor series before, right? Did you do this in calculus? I don't know. Well, this formula here is one way of defining or expressing what the exponential is. So you can use this to put in this matrix here, right? And put this matrix in for each of these x's and x squared, where the x squared is matrix multiplication. So and then you say that the whole thing has to converge. In other words, you have this notion of series as converging. Well, it has to converge for each entry of the matrix. So you have a way of extending this whole story to matrices, but this is still mysterious here. This illustrates the fact that when you think of e to the I theta, it's a rotation by angle theta, right? If I want to know where is e to the I theta, or what number it is, it's like the angle rotated through an angle theta. So that's why e to the I pi over 2 equals I, right? See, what is it? There's a t-shirt that's something like I'm number minus e to the minus I pi. Let me see, is that, get it right? So that's e to the minus I pi. Yes, this is what it is. There's a t-shirt that reads, I'm number minus e to the minus I pi, which is also 1. So it's a worldly way of saying I'm number 1, which for most people would indicate that you're not number 1. Okay, well there's your cultural. I've seen this T-shirt before, but anyway.
I'm just in circuit analysis, like we deal with stuff in the complex plane, but you gotta put the or I've just accepted it as like this. It makes sense.
Well, yeah, and also your phasors or whatever are like they're phase shifts, but you're rotating something by 2 pi. But you're rotating something by an angle, by a phase shift or something like that. But it's in some abstract space. It's like a complex, and part of the
DC circuits, components have there's a real component of impedance.
complex,
The J plane,
right?
The J component.
So the point is that it's useful to put the things in this sort of complex context, because you get some connections between different stuff. So there's something here. The fact that you're represented. It turns out that because the physics of it has to do with the fact that the physics of the circuit elements works out that these rotations in 2x2 matrices are useful for oscillations. So it's basically goes back to the fact that in different homogeneous linear differential equations are oftentimes most simply solved with combinations of exponentials, of complex exponentials. And so, but that's that's sort of the whole mathematics of complex numbers that we don't need. That's too forbidding, because what we have here in this, if we ever get there, complex vector spaces, it does a little bit of complex numbers and shows it doesn't. There's nothing in the chapter is what I just did in the topic with the vec isn't in here. This is just introducing. But the point which you need is factoring polynomials. This is what we need is this theorem that let P of X be a polynomial if D of X is a non-zero, then you can, this is just the division theorem. You can always divide it with a remainder polynomial. And it's like let's see. It's this one here, the fundamental theorem of algebra. Polynomials with complex coefficients or real coefficients factor into linear polynomials with complex coefficients. The factorization is unique. That's what we need. We just need this result. So when we go to the next chapter with eigenvalues and eigenvectors, we're not going to use complex numbers, and we're going to try to have matrices that don't have complex eigenvectors and eigenvalues. Because what we call eigenvalues will be numbers that are solutions of polynomial equations. And to get them, we want to be able to factor them, or at least say we can factor them. Okay, so that's next week. So the whole point, but I wanted to give you somehow make the complex numbers seem more like there was some coherence to it. It wasn't just this, there was some deeper story going on. Okay.
Mission accomplished.
Yes. Okay, well, that's all. So then we can go and so then you'll see, like, instead of R to the N C, you'll have the complex number, you'll see these vector spaces, right? In principle, then you can have coefficients, your vectors could be like I and 1, right? But we're not going to see this stuff. We're gonna start off with like real numbers, and so we won't have to worry about complex numbers. But in the background, there's when you say any polynomial can be factored into linear polynomials, is the background that it's always possible to get a pair of a complex number and its complex conjugate. And okay.